So Mikhail is a research scientist that is working on critical computer vision and generative modeling in Federica Tambari's lab. In 2022, he completed his PhD at Max Planck Institute in Tübingen, supervised by Andreas Geiger. The works occupancy networks and differentiable volumetric rendering were selected among the top 15 most influential papers at CVPR 2019 and 2020, and he received the Best Paper Award at CVPR 2021 for the Giraffe project. So yeah, and personally, to break a little bit protocol, I personally use the Mikhail code, and it's like not only does great research, but the code that he and his colleagues released is like very good to use. So yeah, and yeah, please welcome Mikhail Niemeyer. Yes.
Yeah, awesome. Thanks so much, Dimitri, for the very nice introduction. So yeah, hi everyone. I think it's rather early for you, so thanks for joining still, and also we had like this time shift. I hope you can see me as well. For us, it's here rather afternoon in Zurich, but yeah, let's dive in with the talk. So yeah, today I guess you have like a very cool and diverse set of speakers at your lecture series. Today we will talk about 3D vision stuff, and more specifically, we will talk about like neural representations for 3D asset reconstruction, generation, and also beyond. Yeah, here I show a video where we fly through a house, right? It's located in California. And I would say that most people would think that this is actually a video. However, this is rendered from a state-of-the-art neural field called ZipNerve. And I would say that, like especially with the compression, probably on your side, you cannot really distinguish anymore if this is a video or a neural rendering. So you could ask yourself, okay, is this neural rendering task actually solved? So I would say no. We have many challenges ahead. Just to name a few, first, speed. So the video I showed requires actually 8 GPUs, and then you can render it at 0.1 FPS. Also compatibility. So we use neural networks to do this, but if you open up a graphics software application, you cannot just load this neural field. Also robustness. So here we showed a video. If you zoom in to like semi-transparent surfaces and things like that, they are still not modeled perfectly. And finally, generation. So for creating this neural field we saw, we actually had many images as input. However, you might want to be able to generate from only a few images, or even only your imagination, right? Put into a text prompt. And then finally, we also they require accurate camera poses under the hood, and this is actually something that is in certain scenarios not that easy to obtain. These are things that we want to improve on, and in this talk, I will first present a few works which try to tackle the first part. Then in the second half of the talk, I will go over a few generative approaches. And then at the outlook, we can discuss shortly the last point. Okay, so let's jump to the first part, basically 3D reconstruction with neural fields, where we will cover these two papers. And let's start with the nerve meshing paper. So here the main idea is, okay, we have this neural field and we know we can render very high quality. However, we want to really get this fast, right? We want to be able to ideally render at real time. The approach we took here, which is quite obvious, is can we turn them into mesh representations? So the benefit here is that this would be naturally compatible with graphics software, right? And because of this, we can create cool things that you get for free, like physics animations, for example, that you can just do in Blender or Unity or whatever your software is that you like to use. However, to do this, we actually need physically accurate representations of the world. So it's not enough to just get any type of mesh, but we actually need accurate representations. So let's recap two important related work for this work here. The first one is called baked SDF. It's called baking neural radiance fields. Too many names in this field. It's called baking neural radiance fields. And here, the idea is that you take your big, powerful nerve model in this case, and then you bake it into a representation that you can query very efficiently and fast. In this case, they basically put it into something like a sparse voxel representation so that you can render this very fast. Another different approach, but also gets fast and good results, is called mobile nerve, where the idea now is that you don't have like a voxel-based scaffolding, but you rather use a triangle mesh, which is more like a triangle soup. But then you kind of bake the real appearance onto this triangle soup, and then you can also get out nice-looking images. Now, what these two works have in common, though, is that this underlying representation that you use is not physically accurate. So it's just something that you can render fast on your device or in your software, but it's not an accurate representation. So let's have a quick look at our method. So first, the first question that we asked is like, okay, can you just shift now to training a mesh instead of a nerve model? It's a natural question, right? But the density representation that nerve has actually doesn't support like this unique or single surface representation. There are works which try to do this, but they usually suffer from over smoothness, so they get decent results, but the results tend to be over smooth. And our idea in this work is that we basically want to use a pre-trained nerve model. So the idea here is that you have this very powerful nerve model, and then in a second step, you use this nerve model to now query high-frequency geometry information at certain level sets, and then also query the view-dependent appearance. Now, how this, and then you might ask, or also reviewer might ask, okay, why do you follow such a mesh distillation approach? And here, the key selling point of this is that you can give us any type of nerve model and you can turn it into a mesh, so that we are kind of decoupled from the nerve research, right? So they are like specialized methods, they are like new, better models out there every few months, and you can just plug it in and it works out of the box. And just as we mentioned already, why do we follow mesh-based representation? So that we are compatible with all types of rendering engines out there. This is especially important if you want to serve to not only your machine that you work on, but also something like mobile devices or stuff like that. Yes, and further, you need a physically accurate representation to enable even more powerful tools. So how do we do this? Here we have an overview of the method. So we start with a nerve training, and then we extract what we call depth maps at certain percentiles from the input images, and then we supervise our SDF model basically in a second training step. So what we do here more specifically is that we train a truncated signed distance field. And given these depth maps at certain percentiles, we can basically supervise the area of the where the surface lies in a very, very close interval. So the depth maps here, what we actually extract is that we render array, then we get sample points along the array and weights, and then you can threshold basically at certain percentile values at which point the respective percentile point lies. And so we take the median value as our surface, and then we take small intervals before and after as the like very strong supervision of this underlying surface. And this is the main loss that we use. So it's really this supervision at the surface level itself. Here we want to have it, we want to evaluate our SDF model to 0, right, to be the level set of 0. And then behind and after, we want to evaluate it to minus/plus the truncated signed distance value. And then also we have a normal loss, which is very typical, to ensure that you get smooth surfaces out. Now, we so far only learned geometry. So the appearance, in this case, we do in a second step, where we then learn features on this mesh surface, and then we train jointly a small MLP to do what's called often deferred rendering. So you basically project your point to the image space, to the image space feature that you have at the surface, and then you query a small MLP to predict your color. This way you can get view-dependent effects while being still cheap to evaluate and to render. And here the loss we use is just a normal reconstruction loss. So we already touched on the normal smoothness loss that we incorporate to get out smooth surfaces, and we further also adapt one additional loss, which we call orientation loss, which basically says that because all cameras from where you train are outside of your object, right? No camera is located inside your object. And this means that you can make the constraint that the dot product should evaluate to always point outwards. So the normal of the viewing direction, the dot product of the normal of the surface and the viewing direction should always have a certain angle. And this basically avoids some degenerate solutions, especially in the beginning of training. Cool. So does this actually work? So here we show some example reconstructions. So these are the scenes which are typically used in this field. So it's like outdoor scenes of these rather complex objects. And then here you can see that the mobile nerve approach renders fast and high quality. However, you really get these triangle soups. As you can see here, if you just run something like marching cubes on your nerve model, you actually get quite a lot of artifacts in the room or in your scene, and you get some thickening effects because the model is not trained to have this single surface estimation. And then in contrast, you can see that our method leads to decent reconstructions of the scene. Here we show a rendering of the scene. I'm not sure if you can see it well, but here the idea is that you can now render this representation at acceptable quality, but at very, very fast speed. So this you can get like more than 300-400 FPS on normal machines, because you just exploit this rasterization pipeline that a lot of computers, especially GPUs, are built for. Another aspect here that we wanted to highlight is the ability that you can plug in any type of nerve model. So these are the two baselines with the arrow map on the bottom. And here we plug in the default nerve model at that time, MIPNerve 360. You can see that you get a decent reconstructions. However, here at the where the plant is the pot, right, of the plant, it's a reflective surface. So this is where the normal nerve model struggles a bit with it, so that our reconstructions also are not perfect here. But then we can plug in another specialized nerve method for reflections called RefNerve, which just gets better results for the reflective parts, and we in turn also get better reconstructions. Here we show some renderings of these objects that you can render then in real time. And we mentioned these physics-based simulations. Here's an example where you can put it into Blender and just animate the scene with stuff that you want. So here you can use the power of graphic software together with these reconstructions. So to conclude this work, it's a modular approach that works on any type of nerve model, and it automatically integrates into the computer matrix pipeline, and you can get these simulation and other cool stuff. Of course, we have limitations. So one clear gap, especially if you look at quantitative results, is that you still do not perform as well as these big, powerful volumetric approaches. And because we have this this surface assumption, we do not, and we rely on the NeRF model. It might sometimes struggles with things like reflections or semi-transparent surfaces. And for the last point, we have another work which tries to tackle this aspect, and this is called UniSTF. So here, if we zoom out a little bit again, and we consider what do we actually need to what are challenges, let's say, if you want to reconstruct any type of scene. So of course, scenes tend to be rather large scale and unbounded. So you don't have a single object without any background, right? It's usually you take images with an object, for example, but you have background. Further, a lot of objects have actually quite detailed geometry and you want to capture this. And then the third aspect is that in most natural scenes, there are automatically reflections appearing, right? And there are non-reflective and reflective objects at the same time. So from a higher level, how you can categorize existing works is that one line of work tries, or like, a series of works try to follow the multi-view stereo pipeline. So here, the good thing is you exploit multi-view constraints, and you base everything on this photometric consistency. So you try to do feature matching, stuff like that. However, this is well known to break down for reflective surfaces because, especially here, the appearance is not consistent across viewpoints. Then we also already saw NeRFs, right? And you can base your reconstruction model on this. Popular method, for example, is Neural which these days is actually quite fast to train, and you get fine details. However, we already saw they might struggle with reflections, and some of these reconstruction methods are not designed for unbounded scenes. Then there's another line of work which follows a different parameterization. First of these works is RevNeRF. So they are built to handle reflective surfaces. However, they are often quite slow to train, tend to be over smooth, so they miss details, and we find that the optimization actually can be unstable. So just to recap, NeRF versus RevNeRF, on a high level, the difference is how you parameterize your input. So do you give it the viewing direction of your camera, or do you give it the reflected viewing direction around the surface? So this is the high level difference, which enables RevNeRF to reconstruct actually reflective surfaces. But we find that in the general setup, it's not really stable. And NeRF, on the other hand, is stable, so you can plug it in, but it doesn't really reconstruct the reflection so well. So here it's an ablation study from our method that I pulled a little bit earlier here into this slide because I think it's helpful to understand this. So here you can see on the right side, you can see the reconstruction method that uses the NeRF parameterization. And you can see that for this very reflective car, you really have you really do not model this well, right? On the other hand, like non-shiny and detailed surfaces, you can actually reconstruct quite well. And then in contrast, this other parameterization might be able to model the reflection quite well of the car, but it's not really stable. It might introduce some holes or other stuff like that because this parameterization is not suited for any type of scene, let's say. So the main idea of our work, UniSTF, is that we want to combine these two parameterizations. And then the question is, of course, how do you combine the prediction, right? So then we learn a composition or like we learn a field of these composition weights. And further, we combine it with a grid-based backbone to accelerate the train and speed, which is quite the default case these days, actually. But for these specialized methods, they tend to not do this because it often reduces the quality. So here we have a high-level diagram of this method. So it might look scary, but this here, actually, we should only focus on this part. So you have here inputs and so on. But here, I just want to highlight this part that we really learn these two fields jointly. And also here, this is where we plug in the NGP backbone. So it's like a multi-resolution hash grid to get the features. But now let's look at this a little bit more detailed, what this actually means. So this first field that I mentioned, we call it camera radiance field. So here the color prediction that we have is a function of the point viewing direction, normal, and a hidden vector. And with viewing direction, we really mean this camera viewing direction onto the surface, right? And here we query our function. So this is this one part in our big model here. Then the second part is the reflected radiance field. So here we basically evaluate the point, or we find the point, and then we evaluate our function by not giving it the viewing direction, but actually giving it the reflected viewing direction. This is our second radiance field. And then the third field that we learn is this weight field, where, of course, this is not view dependent. So it just gets the position and normal. And again, this hidden representation that all these methods get, which is a latent vector from the multi-resolution grid. And then how do we do the composition? So, of course, it's the most trivial thing you can think of. It's just this binary alpha blending of the two things with a given weight. And that's the key idea. Now for training, a few things are necessary to get the good results. So our full loss is the reconstruction loss, and then these three additional losses. So one is the iconal regularization. So this is something that all these SDF methods do usually. So it's just an enforcement of the function being an icon, following the iconal constraint, which means that the gradient everywhere should be 1. And then we additionally incorporate this normal smoothness that we already saw in the previous work. And then again, the same orientation loss we also saw in the previous work. Now, one other aspect here that we found crucial is a cause to fine training. So by this we mean, so if you remember that we give all these functions here this hidden vector b, right? And by cause to fine training, we query our grid and give this latent vector to the functions, but we start with like quite low resolution grids, and then over the course of training, we gradually introduce higher resolution grid features. So this way, we get basically better results and more stable training. Okay, so let's have a look at some results. So here, I think, in the interest of time, I can go rather quickly. But the key takeaway is that we basically evaluated on many different data sets because our goal was to propose a general purpose method, whereas most previous works were like specialized methods. So they worked on some data set very well, but then they didn't really work too well on the other data sets. So we first have an object level reconstruction data set where we actually get state-of-the-art performance. Then we have a very shiny object level data set where you can see that here we get nice reconstructions out, even that the toaster, for example, here is extremely reflective. Then on large scale scenes, like the ones we saw earlier, we find that compared to state-of-the-art methods like baked SDF, yeah, we get finer details while being stable. So again, you can see this whole structures that are sometimes introduced for these methods which only follow one parameterization. Yes, this we will see later. And here, this is the ablation study that I showed earlier, right, where we ablate the different fields. And you can see that you can either not model reflections well, or you suffer from unstable training. And then if you combine the two fields, yeah, we find that you get better training for any type of scene. So one interesting aspect maybe is, okay, what does this composition actually look like? And here we show, on the left side, we show individual renderings. And then on the right side, we show the weight of the reflective part. And here you can see that roughly, I would say, the decomposition makes sense. So the reflective viewing direction part is really focused on these parts which are very reflective. On the right-hand side, you can see these very shiny balls, or for the car, for example, the glass and everything that is very reflective is modeled by this one field, whereas the other not so reflective parts, for example, here, this human statue is actually not very reflective. This is rather modeled by the other model. And yeah, here we show some visualizations that you can actually extract meshes out of this representation. And here, this is maybe also interesting. It's an ablation study of this cause to fine training, which we really found important in this work. So this is also the reason, I believe, why most previous works which try to tackle shiny surfaces don't use a grid backbone, although you can get faster training speed, etc. But actually, they often suffer from basically overfitting to the reflections and then getting like these kind of bumps in the surfaces, as you can see here. And we found that the cost-defined training scheme can fix this issue. And the plus side is that you can train much faster. Okay, here I show a video of this one scene which has complex details, but also reflections. I hope that you were able to see it a little bit, at least over the transmission here. But yeah, if you're interested, check out this link, or just Google Uni SDF with our names, and you can find more results on the project side. Okay, so in summary, we showed a general purpose method that you can use for complex scenes that also include reflections, and we obtain relatively fast training and inference. Of course, we have limitations. So one is that we still have the single surface assumption, and another aspect is that we still do not try to model all aspects of the light transport. So here, what I mean is, for example, we would still bake in shadows, for example, right? And of course, the goal is really to go towards this, that you get even more decomposed representations. So now let's shift gears a little bit. And we saw some specialized methods now, right, that can do reconstruction. But we should also ask ourselves, okay, is this actually all that we need, right? And if we look into, also from the company perspective, for example, if we think about, okay, what are use cases? Often, actually, people would like to edit existing scenes. So you have a scene, your living room, your right, your place that you work on often. You might want to edit this, right, for some cool application. So you might want to insert an object. Another aspect is that often, if you give it to users or to people, the way how you capture the scene is rather sparse, and you might even have images captures from different times, right, with different lighting, etc. So you might want to be able to have a method that you can reconstruct, although you don't have this dense coverage. And finally, a lot of works these days as well try to actually go even beyond and say, okay, you get whatever you can imagine by typing in the text prompt, right? So for all these works, what they have in common is that we actually need generative priors. So it's not enough to just reconstruct images, but we need to have some form of prior that we can build on. So here we have 3 works in this direction. I think the first one I will just go over very quickly, which is called text mesh. So here, basically, the goal of this work is, just as you can see here, you want to give it a text prompt, and then you can get out realistic 3D meshes. Here a little bit more defined. So basically, you have an input text prompt, and then you get out as output a 3D mesh that is optimized for this text prompt that you give it. And the applications, are quite numerous. So I guess at least some people of you are, quite familiar, I guess, or heard of all these breakthroughs recently, right? Even with the Sora model very recently, that this space of generative AI is, booming. So I thought it's nice to reflect a little bit how this came by, basically, and also to put this work into context. It's actually not that long ago that people started working on this stuff. And of course, I only talk about 3D generative models here. And one of the first works here that achieved quite general purpose results is called Dream Fields, which were still optimizing a clip objective. They got like rather dreamy results, so not a lot of details and so on, but still it was a proof of concept. And then there were works that tried to move this to a mesh-based representation. And then a real breakthrough was a Dream Fusion paper where they shifted to a score distillation optimization, where you can really exploit large, powerful diffusion models, right? And then a concurrent work to this one is called Magic 3D, which then tries to have like 3 steps to go from your NERF model to the mesh representation. And another aspect of these existing works at the time, which was quite interesting, is that, the NERF model doesn't allow for mesh extraction. And actually the results, as you can see here on the right, these are screenshots, they looked like rather, let's say, cartoonish or oversaturated. If you contrast this to the 2D generative models that you already got at that time, so a year ago roughly, they looked like way better, right? So of course the question is, why does this happen and can we fix this? So here, this is an overview of our method. Let's have a quick step-by-step guidance through this figure here. So basically, we optimize a SDF representation with the score distillation approach. So just for everyone who's not familiar with this, the idea is that you render arbitrary viewpoints. You shoot rays into the scene and you render out arbitrary viewpoints of your scene. And then you add noise to your image, and then you feed it through a pre-trained diffusion model. And this denoises the image, right? And this you can formulate into a gradient formulation so that you can backprop your gradient back to your neural field. So this way, you optimize for the diffusion prior that you give it as in the form of a text input, right? And then in this work, the key contribution was actually that we found, okay, these results look good, but they are often cartoonish, as we saw, and oversaturated. So what we did, we introduced a second stage training where you first extract a mesh and you render canonical viewpoints, and then you actually jointly diffuse these viewpoints again by using another step of the diffusion model. So here you have cartoonish looking images, and then you diffuse them and you get realistic images out. And with this, you can then again train your model and get realistic texture. So maybe I directly jump here to this part. Here's an illustration of this effect. So here on the left side, you can see the initial texture that you have. And then after the diffusion process, you get like this photorealistic results. One aspect that we needed to do is this joint diffusion of multiple views, because if you would diffuse individual views independently, you would have the problem that we show here on the top right, that you would lose multi-view consistency. And of course, we are working in 3D. We want to get meshes. We really need this 3D consistency. So we basically really tie them into like a 2x2 grid, give it to the diffusion model, and then we get out multi-view consistent photorealistic textures. So here, this we can maybe skip in the interest of time. Just some results here that you can see. We can generate, very interesting results from different text prompts, and then applications are AR, VR, and more. To conclude, so this method basically enables mesh extraction from a text input, and it has this mechanism to get photorealistic textures. And another, maybe quickly touching on the last point here, another interesting aspect here, which is really unsolved, is how do you evaluate this now, right? So I tell you, oh, this looks cartoonish, this looks realistic, but it's actually a big problem for this field. How do you evaluate this and quantify this? There are metrics, but they are all not great. We ran user studies to test this in this case, but it's an open challenge. Other limitations is, of course, that it's object-centric, and you only you can only use text as input. So from the last point that you can only use text as input, we have this this work here, Dreambooth 3D, where we exactly want to extend this now, that you basically give it a text prompt plus a few images, and you can generate this this individual that you see in the image, possibly augmented with a text prompt in 3D. So here we built on powerful 2D methods, which allow this what people call subject-driven image generation. So the idea is that you have a few images of, for example, a dog or whatever, and then you fine-tune your big diffusion model a little bit. And then suddenly you have a specialized token, and you can put this individual in all types of scenarios. And we just saw these recent text to 3D models, which also use diffusion models as prior. And then a natural question to ask, okay, let's just combine these two worlds and hopefully it will work, right? But yeah, this doesn't work at all. So if we combine these works, you get something like this here out. So you get something, but it's definitely not what you want. And so in this work here, the idea basically is that we start with a partial Dreambooth. So we have a diffusion model which we adapt very, very lightly to the input images. And this gives us multi-view consistent results, while not really being adhering too much to these input images. And then we have a second step where we again exploit this direct output of the diffusion model. So we basically give it these first stage renderings to an image-to-image translation task, image-to-image translation model, sorry, to predict realistic views from this individual. And then we can use these images in a third step to again optimize our final nerve method. So sorry, in the interest of time, I think I have to go quicker. That's why I went through these steps rather quick. Just to show some results, what we can achieve here. So you take a few images of an object. They don't need to be multi-view consistent. They don't need to be taken at the same location, etc. Right? And then we can get these 3D representations out. And here, baseline comparison, maybe not too interesting. This we can skip. But here maybe, so you can do some cool things with this. So for example, you can take the text prompt and say, I now want to manipulate the material, right? So for example, you can say, can you give me the dog, but made out of glass, for example, or as a statue. And here you can further accessorize the 3D object. So you can give the dog an umbrella or put the cat into a tie, give it a tie. You can do something like color changes, so you can change the backpack different colors. And then this is one of my favorite things where you can put the dog into different poses, for example. So you can ask for a sleeping dog or a jumping dog, etc. So this is all exploiting these very powerful diffusion priors that you have. Okay, so to summarize this work, we propose this 3-stage optimization techniques, and you get this high subject fidelity. And you can use the text prompt to further augment your scene. Limitations here are, of course, these are all rather global changes, and you cannot really edit an existing scene. So I think in the interest of time, I will skip the final work, and I will just jump to the conclusion, where I just wanted to quickly here. I just wanted to quickly summarize the talk. So in the first part of the talk and in the first work that we discussed, we saw how you can take neural fields and turn them into physically accurate meshes. And this is very useful for things like real-time rendering, or if you want to use them in graphic software to animate them or to create physics animation, etc. Then in the next part, we saw how we can develop a method that is rather general purpose than suited to one specific scene. So you can reconstruct fine details, but also reflections. In the third aspect, we saw how can you now move to like the generative world and get 3D mesh assets with photorealistic texture from a text prompt. And then in the last work that we discussed, we looked into, okay, how can you get reconstructions if the input is not just a text prompt, but actually also a few images, which might be much easier to describe something, right? You might be it might be easier to point to this image of the dog that you want to get instead of trying to write it down in text prompt. Okay, so quick outlook on two things, then I will stop talking, I promise. So one outlook, I think, which the field is starting to invest more in, but which is like a very important direction, it's to go towards this, what people call like real-time SLAM. So the idea is that you not only optimize your neural field, but you actually optimize your neural field with your cameras. So all these reconstruction methods, they assume that you have perfect camera poses, which is really not the case for real world scenarios. So in this work that I show here, called DNS-LAM, the key idea was that we incorporate semantic priors to improve the tracking performance, but in general, exploiting these priors, not only generative priors, but other priors, is probably promising to achieve not only real-time rendering as we saw in the first work, but to actually achieve real-time reconstruction. And then the other aspect for like a longer term goal is, okay, we can now reconstruct the scene, and we might be able to generate objects or even scenes. But to really go to, I don't know, more powerful applications, we really require understanding. And here we have a work that tries to do open set understanding. So I really like this direction because you want to avoid the bias that you can only label or understand scenes that you have seen in training. And this work here is one work where it's also trying to exploit large-scale clip models in this case to get this open set understanding of scenes. So we have this plate of like seafood, and you can query for different things, and steak is not visible, so it knows, okay, here we don't have a steak here, but you have these different types of food lying on the table. The model doesn't need it to be trained on this kind of data. Yes, as I said, we exploit large-scale vision priors. And finally, again here, I believe that the understanding of the world should happen in 3D, because then you can really enable very powerful applications in our world. Okay, that's it. I hope I didn't steal too much of your time. Thanks so much for listening. I'm happy to take any questions. Thanks a lot.
So yeah, we have a mic. If people have questions, I will just. Okay. Give me a moment.
Yes, I hear you.
Yeah. Okay. Any questions, Vitas?
Hey, Michael. Thanks for the amazing talk. I have a few questions. I'll maybe just ask one and hand it over to someone else. The first one is on neural meshing. I'm curious, what is your definition of physically accurate meshes or surfaces? Because I'm guessing the output mesh is still a triangle soup with a lot of intersecting triangles, assuming that the mesh is parameterized by triangles. And that's a pretty hard problem to solve in these multi-view reconstruction settings. And so I saw one regularization term, which was to fix these normals, but are there other terms that could ensure you don't get like degenerate triangles?
I think that's a super good question. And I guess we also didn't really define it too well. So by physically accurate, the idea is that I think if you zoom out a little bit, there are two ways how you can use the mesh representation. So in the computer graphics world, if you think of like computer games and you have a car which is driving around, it's really like a designer sat down for hours and designed this car and is like really looking how a car would look like, right? And now in the research world, people actually exploit the mesh representation to get fast rendering, but it doesn't align to this principle that you want to represent your object. So for example, people try to create like rough meshes just to very quickly render the surface, and then they do something close to the surface to get nice looking images, right? So it's basically they use this mesh representation to solve for a different task. And in our case, we really wanted to get a good representation of the 3D object. And then your second question, or related to this, how do you obtain then good representation? That's a good point. It's a really unsolved question how you can mesh the neural fields in a fast and well-principled way. So in our case, the key idea in our work was that we basically first train a nerve model without any type of regularization, etc. So you get the best possible quality, and now we distill it into a mesh where you then enforce priors. And so our prior were normal smoothness. And then also that the surface lies at where the rendering during the density. So I think these are the two priors that we inject. Yeah, and then for the meshing itself, it's really just running marching cubes out of the box. There are works, very recent works, which show that you can do better things. But in this work, we just used marching cubes.
Thanks. Other questions? Okay, then I will ask a question. So my question is, for example, for the methods that do this like kind of 3D distillation from the 2D diffusion models like gene fusion. So you were talking about some generative priors, but my question is like, there is like this interplay of kind of geometry and texture in these methods. And what I observed, like I can't like I just played with such models, but what I observed that the geometry tends to be kind of really bad, and such models that tend to kind of compensate for the bad geometry by like kind of manipulating textures, right? I don't like representing cavities as a like as a textures, for example. And like, what is your opinion? Like, what kind of structural like geometric priors we might need in this case, like to fix this issue? And another, like maybe related questions, like how we kind of control this like interplay of this like kind of geometry and appearance. Makes sense.
Yeah, no, that's a great observation. I think it's somewhat linked to colleagues back from Tübingen, where they had this paper basically, and they showed that neural networks are much more biased to texture than to shape, right? It's like seems to be a general phenomena in neural networks. They are much more strongly focusing on the texture than the shape, or in 3D, the geometry. Yeah, it's a good point. So I guess it depends on the task. I think for some tasks, people actually want this. So they want to rather bake every complex stuff into the appearance, because this way you can store things much more efficiently. Because appearance, if you unwrap it, it's just 2D, while the 3D stuff you need to store in 3D. So you want to move any type of complexity ideally to texture, to the 2D space. And then how can you fix it? Yeah, it's a good point. I think the best result so far that I saw is that you need to make the geometry prediction part more expressive. So in the reconstruction part case, what people do is that they don't use an MLP, but they rather use grid, different grid level representations, right? To be able to represent high frequency geometry information. And I think you can exploit more there. But yeah, it's an unsolved question, and I don't have the perfect answer, but that's, I guess, one way to go about it.
Oh, thank you. And you actually kind of touched another question that I wanted to ask. It's my understanding that the geometry in the NERS is usually modeled by MLPs, and you mentioned some like grid-like. So recently, since I work like more on the geometry, there's like the powerful approaches to introduce like 3D shape to vector. It's like the model geometry as a like regular latent grid. But my question, because you understand this like kind of computational part of this better, like we kind of have like two things here, right? One thing we want to, if we want to model geometry, we can use a regular latent grids, but on the other hand, there is like this computation issue. And like in your observation, is like kind of how much of a bottleneck this kind of geometry part, like computation-wise, and it's like how much of an overhead this like regular latent grid might introduce. So we're kind of paying for like better geometry with the like how much exactly, how more computation it makes sense.
Yeah, no, that's a very good point, actually. So I think one interesting works that I found is that people try to move the reconstruction to the latent representation itself. So what I mean by this is if you consider stable diffusion, you have a big RGB images, like, I don't know, 512 by 512, but then in the latent space, the resolution is much smaller, right? So people, there are line of works which try to do the reconstruction on the latent level so that you can move, like you can have more complex architectures on the 3D side because the supervision signal is on lower res, but potentially better, more compact due to the latent representation, right? And the other aspect which seemed to work well, even from the earlier GAN works and also from some diffusion models, is that you try to move some of the capacity to 2D. So what I mean by this is that you can imagine that you do your powerful volume rendering on a smaller resolution, and then you have a 2D upscaling module mapping it to your higher resolution. And this way, again, you can trade off some of the complexity to make your model bigger. In 3D. But in general, I agree. Just scaling voxel grids, latent voxel grids, higher and higher doesn't seem to be the solution. And I guess there's still a fight out there of what is the best representation. Right now, also with Gaussian splatting, people shift to this. So I think we still need to see what's the best representation to do this.
Yeah, thank you. So it's 1 p.m., but I think depending on your time, we might have time for like one more question. One more speakers.
Yeah, sure. If we have a question more, I'm happy to take that.
Yeah.
So one of the limitations you had for I forget the name, the second paper that you presented. And you said the limitation was that it doesn't model the entire light transport. I'm guessing that's effects like caustic effects and subsurface scattering. So would the solution be to just have explicit MLBs for each of these effects, sort of analogous to the rendering equation where all of these terms have to be explicitly written out, or is there like some unified neural architecture that will present all of these for you?
Yeah, that's a very good question. So I think, so what I meant by this is exactly what you described. So I guess we, at least the 3D vision people, they try to, whatever, like however you currently create like a Pixar movie, right? You start with 3D object and you have so many complex effects. And this you kind of want to be able to infer now from multi-view images, right? So one aspect is light bounces, right? And one object casting shadow onto the other, etc. I think, however, there is some limitation of what you can really infer from 2D images. Yeah, I think there are multiple approaches towards this. I think a very nice interplay. I haven't seen too many works here, but again, using 2D priors to do this. So what I mean by this is you could imagine utilizing again your big diffusion model somehow to say, oh, this should be a shadow cast or this should not. So we saw this in like some insertion work where we have a scene, we insert an object, and then sometimes the diffusion prior really says, oh, this doesn't look realistic. You want to cast a shadow here, right? So I personally, I'm a bigger fan of training your 3D model on the data you want while exploiting very large 2D diffusion models, because the other option would be that you train very large models on 3D data, right? But 3D data is not as diverse as, and not, we don't have so many good examples compared to photos, right? Because everyone's taking photos all the time, but 3D models are created artificially, right? So I personally think that this interplay of 3D physically inspired priors and large-scale 2D image models seems to be a promising way to further model more aspects of the light transport.
Thank you. I think we're out of time. Let's thank Mikhail again for a wonderful talk. Yeah, and thanks again, Mikhail, for giving the talk. And yeah, it was absolutely wonderful. Yeah.
Thanks so much, everyone, for being here in the Zoom room. I really appreciate it. And yeah, have a great day. See you guys.
Bye.
Bye.
do and I'll do the same thing. Second, if you do and,
okay,
go
sure.
down to the bottom to do that.